Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In the previous video we learned about decision trees. We had that general introduction about decision trees. In this video we're going to discuss how decision trees are more prone to overfitting than probably a few of the other algorithms that we have seen so far, such as linear regression, KNN and naive Bayesian, and see what are the mechanisms that decision trees have to combat this overfitting problem. Alright, let's look at the video. Alright, so in this video we are going to first discuss some recap on what decision trees are. So like we are our mind is where it's supposed to be, and then after that we're going to discuss how is it that decision tree needs combating overfitting, and what is it about decision tree that allows this to happen. And then we're going to discuss pruning, which is the mechanism of decision tree to combat that, and we'll wrap the video with a summary. So as we remember, when decision tree sort of start like in the induction algorithm, as we saw, it starts from the whole data and it starts filtering the data, splitting the data based on some of the independent attributes, one of the independent attributes, and continue going down and start to have subsets of the data that are purer and it's useful for the purpose of classification. So this is what we have seen already. So I'm just like going over them so you remember. Decision tree basically keeps splitting the data until it gets to a point that the leaves, which have the subset of the data, are pure enough for us. So that's decision tree for us. So this was the trained decision tree. But now from starting the material that we want to cover in this video, overfitting, it's a phenomenon that can happen to classification algorithms that are sort of like aggressive towards a decision metric, or aggressive towards a metric that is trying to sort of like create those relationship between the independent attributes to the dependent attributes, and does this learning by looking at the metrics that are going to be improved along the way, right? So since decision tree uses the purity metrics that we discussed, and it can grow as fully as possible until each node or each end of the tree is one data object, the decision tree is prone to overfitting. And overfitting, what we mean by that here is the model, in this case decision tree, is not really capturing the pattern of the population, it's capturing the patterns specific to the train set. And that's not what we want. What we want is generalizability. We want to be able to generalize the pattern we get from the train set and be able to use it later on, right? So overfitting happens is when the patterns we have selected for later use are specific to the train set, and that's not what we want. This is going to lead to not successful prediction. So that's overfitting and why decision tree is prone to it and what we are going to do about that. So that's overfitting, and the mechanism, as we discussed, for decision tree to combat overfitting is known as pruning, tree pruning. Let's compare pruned decision tree and non-pruned decision tree. Non-pruned decision tree is the fully grown decision tree on the left, and it's normally bigger, it's larger because it has more branches and more depth, and the pruned tree is smaller. Also, the non-pruned tree is more complex. Understanding it is probably harder than the less complex pruned tree. But more importantly, it may sound counterintuitive, but if you have taken the time to prune your decision tree, it may look like sort of like simpler and smaller, but it's also going to be more successful at prediction. It's going to be a more reliable predictor. So there are two approaches. We call them pre-pruning, or actually, I mean, they're not pre-pruning. They're just like, they don't let, I mean, this approach of pre-pruning, they don't let the tree to grow all the way, right? So it's called pre-pruning because it wants to come against pruning, but it's actually, tuning the hyperparameters of the decision tree algorithm. And then we've got post-pruning where, we let the tree grow all the way, and then we come back to sort of like see what are the branches that we can cut. And the idea of pruning really comes from this area. I mean, we have the fully grown tree, and then we start cutting some of the branches, so that's pruning for you. But here we call it post-pruning, and the pre-pruning one is actually just tuning the hyperparameters of a decision tree algorithm. So let's talk about the pre-pruning first, and then we'll discuss the post-pruning. Basically, like I said, pre-pruning is tuning the hyperparameters of the decision tree. And one of the things that we have to learn in this area of data science, there are many different algorithms here and there. MATLAB has different algorithms. Python has different modules with different algorithms. R have different algorithms. Each of these algorithms, while they do use that general induction algorithm that we discussed in the previous video, they have a little bit of differences in the way they work and in the way they are suggested to work. So for example, the Python module, as the most famous decision tree module, uses these hyperparameters. And for you to be able to have a successful decision tree with Python, the sklearn module decision tree, you actually have to do it with pre-pruning or tuning. You have to tune these hyperparameters, and that's how you're going to be able to have a successful decision tree. But with R, you have to go through the post-pruning. You have to let your tree grow, and then sort of like use the a mechanism that we will see in the next video to prune it and make sure that it's not overfit to the data. Some of these hyperparameters might be a little bit different from one algorithm to another. I mean, all of them are decision tree, but from one software to another. But here we're going to discuss the hyperparameters for the Python sklearn module decision tree, and these are the 5 hyperparameters that we'll go over right now in this video. So the first one is criterion, which is basically the impurity metric, and Python supports Gini, which we saw in the previous video, and also another impurity index or metric, which is entropy. So that's all there is to it. You can choose between one of these two. And then we've got splitter. The Python can do the splitting randomly or choose the best one. In the previous video, what happened was, do you remember when we were trying to find the attribute test between these 3 possible attributes? What we did, if you remember, we calculated the sort of like what would be the impurity if we split the data using this attribute, right? So we get to 0.25, and then we calculate this one, we get to 0.4, I believe, and calculate this one, we get to 0.4 something, right? So we were able to sort of decrease the impurity for if we were to split all of them from 0.5, but when we choose the best, like when we use best, it's just going to use this one, right? So that's the best approach. It's going to use the attribute that leads to the best impurity decrease, right? But the random one sort of select the next attribute randomly. But the way it does, it's not complete randomness, as in all of these 3 attributes are going to have the same chance. It's going to do it by sort of like having a probability value that is sort of proportional to how well or how much impurity decrease it's going to happen. So for example here, it's going to calculate the probability measure. Since this leads to the best best impurity, it's going to calculate an importance value. So let's say the importance value is going to be 0.5, and then these two is going to be 0.25 and 0.25, right? So based on these importance values, it sort of like allows all of them have a chance to be selected, but the chance of customer income, because it leads to a better impurity decrease, is higher. So that's the idea of, the random splitter, right? So sometimes it's sort of like it's better to open things up, instead of like saying going with the best. Who knows if you split with something else, that might be better. I mean, because this is a heuristic algorithm. It's not. I mean, if you see it start splitting, right? You don't know if one split is going to be the best in the long run. So that's why if you go towards the random approach, you're sort of like keeping your options open, right? So that's basically the idea of having a random splitter. But something to remember, in the previous video, we did assume that splitter was best. All right, so let's move to the next hyperparameter. It's max depth. It's basically how deep you are allowing your decision tree to grow. If you put the max depth at 1, this is going to be as deep as your decision tree is going to be. Like, it's going to have 1 level down of the root. If you got max depth 2, it's going to be 2nd level, and so on and so forth. So it's basically a way to not allow your decision tree to grow as further than a specific depth. The next hyperparameter is mean sample split, which is as written here, the minimum number of samples required to split an internal node, right? Every time we want to split, in the beginning we had all the data, but at any split node we had a data set, right? Every time we want to do the splitting, we have to check if this has enough required data objects for us to split, right? For example, here, if we have the mean sample split at 6, and we are here at this possible splitting point, and we check, we've got only 5 data, right? Therefore, because 5 is smaller than 6, the algorithm will decide we cannot continue splitting, right? So this is a leaf node, but it's a leaf node that, even though most of the data objects are yes case or yes label, but there are still 20 of them that are no table. So we stop right there, right? So that's the idea of mean sample split, right? So you need to have at least a certain number of data objects in that split for every split. So that's what it is. The next hyperparameter is min impurity decrease. This one is when you do the split, it's going to be accepted as a split if it leads to equal or larger impurity decrease, right? If your split leads to an impurity decrease that is smaller than this threshold, we basically don't do the split. Let's see an example. So for example, let's assume that our minimum impurity decrease is 0.1, and we calculate the Gini index, which is our impurity metric for this data, this subset, and it's 0.32, right? And then we also calculate the best possible split that we had seen. If we were to split it like this, our Gini index of our split would be 0.2, right? So when we do this split, we move from 0.32 to 0.2, right? And we are improving by 0.12 our impurity, right? So since 0.2 is larger than 0.1, which was our minimum impurity decrease, we let this split happen. So because of this, we let it happen, this becomes another splitting node, right? So this became another splitting node, and we get to this is pure, and then we have to continue here, right? So that's how we decided to do this to go on. I mean, this is not what we did in the previous video. This is what I'm just sort of like telling you what would happen if our minimum impurity decrease was this one. So so far we learned about the pre-pruning or tuning the decision tree. We saw 5 hyperparameters, and together, if you tune a decision tree with all of these five hyperparameters, they are very effective. I mean, for, if you tune it with all of these 5, which the tuning process might be time consuming. But if you actually do that, it's very effective in combating overfitting, because all of these 5 different hyperparameters, they have a different spirit. They are sort of like controlling the growth of the decision tree in a specific way. So when you combine all of these together, if you tune the decision tree algorithm this way with all of these hyperparameters, it's going to be a very effective way to combat overfitting. So this is the difference between non-pruned tree and the pruned tree, right? So we sort of pruned it here, and now this is sort of like been decided. For example, this is just an example. So now let's look at the next pruning approach, which is post-pruning. And here we let the tree to fully grow, and then once that happened, we sort of like prune it. Actually, this is where the name comes from, right? So that's basically what we do. We let the tree grow, and then based on a specific procedure, which is basically using a test set or a cross-validation to find the error rate for each of these locations, or each of these candidates tree that have it pruned. So some part of them have been pruned, right? And we calculate the amount of error based on the validation set, right? Based on a set that the validation set or a pruning set, which is not the data that the decision tree used to grow, right? It's the data that is new. It's not a test set, but it's going to be used to make sure that the decision tree hasn't grown too much, or it basically hasn't overfitted, right? So that's basically the mechanism. And in the next video, we're going to actually do a decision tree in R, and we sort of see how that is done in R. Alright, so let me wrap this video up with a quick summary. In this video, we talked about overfitting and how decision tree are prone to overfitting, and we learned about the pruning, the different 2 approaches of pruning to combat overfitting. Alright, until the next video.